I just want to finish off quite quickly on soil carbon. And this is another area that attracts an enormous amount of interest. And I think it's an area where there's a lot of misunderstanding as well. And there does often seem to be a feeling out in the sector that soil carbon is increasing because we manage our pastures well, we farm very well, and so our soil carbon must be increasing. And so I'll just, in a sense, try and give you an up-to-date picture of from the information we have. So first thing is, is soil carbon in itself an important issue? Globally, there is more carbon in the soil than there is in the atmosphere. It's a huge sink. And in New Zealand, these are some survey results that have actually measured soil carbon in our agricultural land. And you can see we're actually having values around that 100 tonne per hectare. And that's measured down to a depth of 30 centimetres, which is a standard depth we use in general for soil carbon, because below that it drops off quite rapidly. So, and in international terms, that's very high. It's about 6% roughly of the organic matter. Soil organic matter is about 6% carbon. If you go to somewhere like Australia, it will be less than 2%. So it does depend on the environment and the basic soil type. But we are high by international standards. We have got a lot of permanent pasture. We manage our soils very well. We have this sort of benign temperate climate. So our soil carbon is high. So we start from a very high base in terms of how much soil carbon we have got. Then how do we add carbon to the soil? And what do we mean by soil carbon? When we're talking about soil carbon, we mean stable carbon, the carbon that will stay in there in a stable form for hundreds and hundreds of years. There's a lot of soil carbon goes in and out, as I will show, but we're looking at how much soil is there stabilized in soil aggregates and remaining there for long periods of time. So how do we get carbon into the soil? We can only get carbon into the soil in general via photosynthesis. We actually have plants photosynthesizing, they put material carbon into above ground structures and below ground structures, and then some of that below ground carbon that is put in from photosynthesis gets stabilized. Now, of course, in a system, it's a very constant turnover of carbon. This is some data just to show the sort of size of these fluxes of carbon. Very average situation here. The numbers are illustrative rather than demonstrating any particular situation. And we often talk about in terms of carbon, not in terms of carbon dioxide, but we get about 20 tons of carbon being taken out of the atmosphere by photosynthesis. And this is on a hectare basis. But immediately plants respire. That means they're releasing carbon, and about half of that immediately gets released. So of that 20 tons taken out, very, very quickly about 10 tons goes back into the atmosphere. Doesn't ever enter the soil, really. Not in any great form. Then we've got this net photosynthesis. This is the material that gets put into plant structures, is around about 10 tons per hectare. Of that, about half goes into above ground structures, and about half goes into below ground structures. Now this gets eaten by animals, or it gets eaten by us, and then we'll respire, and that goes off again as carbon dioxide, and then some will go below ground into roots and litter. Now and then how much of that, this is the big question, this goes down below ground, how much of it goes off into the atmosphere? If we are not changing the soil carbon, all of this that goes below ground is coming back off. It's a soil microbial process. There's microbes in the soil that are constantly turning over this carbon. For it to be gaining carbon, of course, we need respiration from the soil to be less than that 5 tons we put in. To gain it, if we're losing soil carbon, the amount respired would be more than that amount we put in each year. Very hard to track that. It's not easy. The tracking the above ground is much easier. So I'll just go to what happens above ground, and this reinforces a bit what I said earlier on, that we're always tracking, and all our understanding is trying to have a mass balance. So we have to account for all the carbon. Some's coming in, some's going out. So of that carbon eaten, some of the carbon goes into urine and feces, and then that goes into the soil, and then a lot of it goes on the surface, particularly fecal material goes onto the surface and just simply respires off the surface. There's a certain amount goes into animal respiration, milk and meat. Some of it goes off as milk and meat that you, I, and others eat, and we respire the carbon out of that. And there's this small amount gets converted to methane. So we can track the carbon very well from the above ground structures. Much more difficult to find what's going on under the ground. So what influences what's going under the ground? How do our management practices, how do external factors, environmental factors influence this? And basically, how much we take out of the atmosphere and put into the ground depends on things like the climate, depends on, it could be additional moisture from things like irrigation, how much nutrients we apply, what the soil pH is, and as plants grow, they're affected by the carbon dioxide level in the atmosphere. They all affect how much goes into the soil, and they affect how much of this below ground, how active the microbes are that turn over carbon in the soil. And then we have respiration processes, which are basically governed by the same thing as photosynthesis. So to gain soil carbon, we literally have to be getting more carbon going into the ground than we get off in respiration, and it will depend on what's happening with these soil microbes and how they can stabilize it. So are we in actual fact gaining soil carbon? We understand how you take carbon in and out. Quantifying what's happening is very difficult. What it is that carbon accumulation is relatively slow. You'll be gaining or losing carbon in general quite slowly. But we have this very big stock, so we might have 100 tons a hectare. So if you're trying to measure it, you're trying to measure generally small changes against a very big stock, and that's very hard. And so you have to measure frequently and across very wide geographical areas to get an understanding of whether soil carbon is going up or down. So nationally, what do we know? Basically, we know that from our measurements, which are not that comprehensive, and I'll explain why soon, that for large parts of New Zealand, particularly on our flatlands, under dairy, under sheep, on the flat to rolling lands, our measurements tell us we're not changing carbon at all. It's in steady state. There's carbon going in every year, but there's as much carbon coming out. We are not changing the stock of carbon. It's at steady state. We know that in some soils, particularly these high carbon soils, peat, which is close to 100% carbon, and some of these higher carbon allophanic soils, there are losses of carbon from the soil. We're seeing our carbon going down. On the other hand, from measurements we made on medium slope hill country under sheep and low input sheep and beef grazing, we're actually recording some increases in soil carbon. So the picture is very patchy. Some areas it's not changing, some areas it seems to be going up, some areas it seems to be going down. When we put that together nationally, it seems as best we can guess, or best we can measure and estimate spatially, that we're actually, across the country, we're neither going up or going down. We're very much in a steady state with respect to soil carbon. And that's very disappointing for many farmers who feel that they're increasing soil carbon. Now, it could be that some individuals are, but on the other side, there'll be other individuals who are actually losing it. We're just saying that based on the evidence we have, the only thing we could conclude from that evidence is that we are in actual fact in about steady state averaged across the country. So we're not gaining or losing carbon. Very disappointing because there's a lovely figure you can quote very simply. If we gained 1 ton of carbon in the soil per hectare across the whole of our pastoral grazing hectares, around about 10 million, we would offset every single methane and nitrous oxide emission. So all we have to do is get 1 ton of carbon per hectare. Sounds really, really easy when you say it like that, but as far as we can see, it's actually not changing. And there are some other issues that you can lose carbon very, very rapidly. If you have a very severe drought for a short period of time, and then it wets up again, what you often do then is have a lot of material in the soil for the bugs to work on, and the bugs, when it's moist, then work very fast, and you might have gained carbon for 10 years in a row, and then you can lose it all inside 6 months. So it's a very dynamic system. So when you're looking at soil carbon, it has to be measured over long periods of time. So what can we actually do? We certainly can tell you what will decrease carbon. We know if you're in cropping and continuous cropping, when you're disturbing the soil on a frequent basis, we'll lose soil carbon. So if you measure carbon under an arable soil, it will be a lot less than if you measure it under a pastoral soil for the same soil type in the same location. So cropping itself tends to lose soil carbon. There may be practices within cropping that can minimize that loss, but in general, we continue to lose it. This is an odd one because you'd think irrigation would increase the amount of dry matter you produce because, say, for grass growth, it's dependent on water. So if we put more water on, don't we in actual fact produce more grass, more roots, so we put more carbon in? Why does it go down? What seems to be happening, and we've measured this now quite comprehensively across the country, is that when you look at soil carbon, you've got to look at the balance between photosynthesis and respiration processes. And you put irrigation in, you increase above ground, but the amount of root below ground actually doesn't increase in the same proportion because you've constantly got a moist soil, you don't put roots down quite as much. So you're not putting as much down as you think you ought to be for the increase in the above ground dry matter you produce. Allied to that, the moisture increases the activity of soil microbes. So seemingly, we get a bigger increase in microbial respiration than we do in the input of carbon to the soil, so it starts to go down. And that was a very unexpected finding. Now, that doesn't mean if I had a very low input soil and I then put irrigation in that I wouldn't increase it. I probably would. These examples are taken from soils in the same location that over long periods of time have had irrigation versus no irrigation with similar farming systems. So it doesn't apply necessarily to if I convert from one to the other. It applies that if I have a long-term steady system. Just on one kind of basic principle, and this applies very much to things like reseeding. If you're reseeding pasture from one time to another, bare soil loses more carbon than does a vegetated soil. So if you're reseeding, you want to reseed in a way that you can minimize the amount of fallow time. You want to minimize the amount that you don't have vegetation. And we also know that if you're reseeding, it can be a zero-sum game if you have relatively long intervals between reseeding. You'd reseed a pastoral soil, it would lose some carbon, but then over the next few years, as the grass established and you graze it, it would gain that back. So Louis Schipper, who's probably done most of the work in New Zealand, says he thinks it's about 4 to 5 years between reseedings when you in actual fact are in a zero-sum game with respect to soil carbon. If you want to measure soil carbon, you are measuring it more in decadal timescales because it's a bit like trying to say, is the temperature increasing? And you say, well, hang on, the weather changes all the time, but how do I pick out whether there is a temperature increase? You need long-term temperature records because you have to get a trend from a large temporal variation. And the same with soil carbon. So we are just at, in actual fact, I got approval for this, funding approval for this yesterday, that we want to set up a long-term soil carbon monitoring program in New Zealand. We'll be monitoring across around 500 sites, sampling to a depth of about 0.3 of a meter, using standard protocols both for the sampling and the measurement, and we're going to do that for 12 years. And at each site, we will measure 3 times within that 12 years. And this will be the first time anything like this has been attempted. Within that, we do have enough sites to say for different land uses, dairy versus horticulture versus cropland versus hill country, we will be able to pick out whether those individual enterprises or individual farm types are also going up or down. So we do have some finer level detail we can get. It won't go to the level of individual farms, that's a very different issue, but this should give us a national picture of whether soil carbon is going up and down. The current information we have is very, very sporadic. We've sampled over time, but not necessarily in the same places. We have in some. We've not necessarily used the same depth. We've not necessarily used the same analytical methods to measure soil carbon. So we just don't have a robust and comprehensive time series. This is setting out to do that. The reason why it hasn't been done before is purely financial. This program of work conservatively will cost us about $7.5 million, cost the government about $7.5 million. So it's not an inexpensive process, but we need it because otherwise we're guessing. We have got some data, we all recognize it's not adequate. If we want to answer this question, we have to undertake this kind of comprehensive sampling routine, and that will start within the next month. So if we come back here 12 years' time, I'll give you a better answer as to whether we're actually increasing or decreasing soil carbon.